So hi everyone, this is Raj. In this video I will be talking about the thermal velocity and the drift velocity within a semiconductor. So let's start with the thermal velocity. So what is thermal velocity? Thermal velocity this is the velocity of electron or holes due to temperature greater than 0 Kelvin. We have studied in kinetic theory of gas that there was a formula E equal to kT, where K was the Boltzmann constant, T was the temperature in Kelvin, and E was the not energy, it is the kinetic energy of the particles. So if we put T equal to 0 Kelvin, that means absolute 0 temperature, E equal to 0, that means the kinetic energy of particle gets 0. That means the velocity, because kinetic energy that we know that half mv square, that is 0, that means v equal to 0 because m is not 0. So v is 0, that means particle at its stationary state, but any temperature which is T greater than 0 Kelvin, then E not equal to 0. That means half mv square is not equal to 0. That means V is not equal to 0. This means the velocity of electrons and holes due to the temperature greater than 0 Kelvin is the thermal velocity. Actually, I told about this thermal velocity in, I guess, second or third video of this lecture series, where I told about the motion of electrons under, without any external electric field and with any external field. I classified the whole discussion into two sub cases. One is under electric field and another one is without any electric field, the motion of electron. So where I told about the motion of electron without the electric field, then there I told about the velocity, about the motion of the electrons, and I mentioned the name that the velocity of the electrons without any kind of external agent is known as thermal velocity. So yes, so you can see any temperature, at any temperature which is greater than the absolute 0 Kelvin temperature is at that temperature we can find velocity of the electron and hole, and that type of velocity is actually known as thermal velocity. So I will do some mathematics right now. So at any temperature which is greater than 0 Kelvin, the motion of electron is random, because at any particular point of time the electron has equal probability of moving in all the directions. I mean, it has equal probability of moving in any direction. So but at last it will come to its primary state, primary position, and then it will go for another random path. So this type of motion is known as Brownian motion. This type of motion is called Brownian motion, and the velocity at which this electron is moving is known as the thermal velocity. So within a semiconductor there are some free electrons, and also there are some immobile ions. In my last video I was talking about these immobile ions, that they are immobile because they are bounded with the other crystal structures. So they are immobile, they are bigger ions, but the electrons which are free electrons, they can move easily. So this and each and every one of this electron has its unique Brownian motion. So suppose at any particular time this electron is moving with u1 velocity, this electron is moving u2 velocity, this electron is moving u3 velocity, this electron is moving u4 velocity, this is at u5 velocity. So each and every one of these electrons are moving, and they are following their Brownian motion, their random motion. But the average value of thermal velocity is equal to always 0, because if the electrons are moving, each and every one of the electrons are moving and they are following their Brownian motion, their random motion, and if the summation of all the velocity is not equal to 0, then there must be a current. Because what is current? A net displacement of electron from one place to another place. That is the root cause of current. But in practical world we see that if we are not giving any external force or any external electric field to the semiconductor, then we can't find any current across the semiconductor. So of course it is a rule of nature that the average value of the thermal velocity, it must be equal to 0. Otherwise without applying any external force we can get a current. So the energy conservation rule would be broken there, because it is not possible. If there is the velocity of all, summation of all the velocities of all the electrons are not equal to 0, then there must be a displacement, a net displacement of the charge carrier from one place to another place, which will cause a current. But if we are not giving any external force, then how can I get a current? There is no possibility of getting any current. So of course the summation of all these velocities must be equal to 0. That means the average thermal velocity, which is u1 plus u2 plus u3 plus dot dot, suppose there are n number of electrons, so un divided by n, that is equal to 0. So this is the this is the information about the thermal velocity, what we exactly should know. So now I will deal with drift velocity. So again, I will say that in my second I guess it was third video of the video lecture series, where I told about the electron's motion in under any external electric field. There I mentioned the word drift velocity. So we will study drift velocity in detail here. So what is drifting? At first we should know. So drifting is actually moving of a particle due to any attraction or repulsion force. Moving of any particle due to any attraction or repulsion force, that is called drifting. That means here we should deal the semiconductor under any external electric field. Suppose the semiconductor is now connected with a voltage source. It is higher potential, and this is lower potential. And of course there are some ions, immobile ions in the semiconductor, and there are some free electrons also. So now we will try to understand the internal operation or internal working or I will say internal motion of the electrons under this external electric field. So suppose the value of electric field is E. So the force which is acting on each of the electron will be minus QE, and if the electric field is absent, if we are not connecting any voltage source with the semiconductor, then there is an initial velocity which is known as thermal velocity, that is present within the present within the semiconductor, that is present with the electrons due to their Brownian motions. So the thermal velocity is actually the primary velocity, and that is denoted by U. And if we consider the drift velocity, is V, and the drift velocity is due to the pulling force of the electric field on the electrons. So due to the drift velocity, the electrons are getting pulled in the opposite direction of the electric field. The electrons are experiencing an acceleration. So if we talk about the acceleration, then of course we know from Newton's second law that force equal to mass into acceleration, and from here we know that this force is actually q into minus q into e, that is ma. So the acceleration value is minus qe divided by m, but we will write it as q a equal to minus q e by m star, and this is the mass of electron, so I will denote it as me and star to define the effective mass of the electron, because as the electrons are moving within the semiconductor, and they are feeling different type of forces within the semiconductors, because one force is due to the electric field, one force is electron repulsion force, one force is electron and some positive ion, the attraction force between the electron and any positive ion. So there are a lot of forces which are acting on each one of the electrons. So the electron which we are dealing with, it is not in its stationary state. So that is why we are not taking its stationary mass value, we are taking its effective mass value. So that is why I have put a star over there, and I have put E because it is the mass of the electron. So that is why we are using the effective mass concept in this formula. So now we will try to visualize the drift velocity in a more detailed manner. Suppose this is one electron and this is one atom in the semiconductor. This is one atom in the semiconductor. This is one atom in the semiconductor. This is another atom in the semiconductor. This is another atom in the semiconductor. So suppose without the electric field, in the electron was having only its thermal velocity, so it can move in this way. Suppose it is going here, then it is taking place with a collision, it is colliding with another atom, and then it is coming in this path, it is colliding with another atom, and then suppose it is making a collision with this atom, then it is going in this direction, making a collision with this atom, and then it is coming in this way. But okay, so this scenario is when the electric field is not applied. So this is the scenario when the external electric field is absent. But right now, suppose I have given an external electric field here. So what will happen, the thermal velocity is always present with the presence of temperature. So what will happen in absence of electric field, the electron would go in this way, but as there is an external electric field is applied in this direction, the electron will move in the opposite direction of the electric field. So it will move in this way. So as this is the positive side, so higher potential side, so electron will go in this way. It will not collide with this atom, it will make a collision with this atom. Then suppose it is coming towards this. Now again it will be pulled back towards the left side. So it will not again collide with this atom, it will collide with this atom. And again, suppose it is going here, suppose it is moving in this direction, it will pulled again and it will collide with this atom. So as you can see, the path I have denoted with the straight arrow, that is the path followed by the electron in absence of the electric field, and the dotted path line is actually the path of the electron in presence of the electric field. So as you can see that the electron is experiencing attraction force, and it is feeling an acceleration. So in our kinematics, what we studied in our 10+2, that the final velocity is actually the initial velocity plus acceleration into time. So here the drift velocity is the final velocity, and initial velocity is the thermal velocity, which is denoted by u, and acceleration is actually we have calculated, we will put it later, and t is actually the time period between the two collisions. So that is denoted by tau. So v is equal to vd, that is final velocity, and that is drift velocity. U is the primary velocity, and this is actually the thermal velocity, and tau is the relaxation time. The time taken by the electron between two successive collisions. And a is of course the acceleration. Which is minus QE divided by ME star, where ME star is the effective mass of electron. So up to this I think everything is clear up to this to all of you. So now we will find out the relation and a mathematical expression of drift velocity. So right now we were talking about one single electron. So for that, drift velocity was thermal velocity plus acceleration into relaxation time. For second electron, the thermal velocity of the second electron plus acceleration of and the relaxation time of the second electron. The same way, the third for the third electron, the drift velocity will be the thermal velocity of third electron, acceleration into relaxation time of the third electron. So this is how, if we have n number of electrons, then we have this. So the average drift velocity Vd, it is V1 plus V2 plus Vn divided by n. So if we put the values, then u1 plus a tau 1 plus u2 plus a tau 2 plus u3 plus a tau 3 plus un plus a tau n divided by n. Now we will combine all the u1, 2, 3 up to n. So we will write it in this way: u1 plus u2 plus u3 un divided by n plus, if we take common a from all the terms, then tau 1, tau 2, we write it in the next line, plus a into tau 1 plus tau 2 plus tau n divided by n. So Vd, okay, so this is actually the average thermal velocity, and the average thermal velocity u is equal to 0, that we know. So we will put 0 a, and this is actually average relaxation time. This is known as average relaxation time. So it is denoted by tau. So Vd equal to a tau. So now we know the value of a. So Vd equal to minus q e tau divided by me star. This is a very important relation. So this is the expression for drift velocity of semiconductor, and here the tau is the average relaxation time. So this is everything about the thermal velocity and drift velocity of semiconductors. So thermal velocity is the velocity in absence of the any electric field. It is, I mean, thermal velocity is only related and linked with the temperature at which the semiconductor is in. If the the temperature of the semiconductor increases, then automatically the thermal velocity increases. But drift velocity is not related to the temperature, because it is all the thermal velocity term is get cancelled, and the value of the average thermal velocity equal to 0. So that is why there is no temperature term related to the drift velocity. So the thermal velocity is linked with the temperature of the semiconductor, and drift velocity is the velocity due to the external electric field which is applied across the semiconductor. So reason of both of these velocities are totally different. So try to remember the basic difference between the drift velocity and the thermal velocity. So thermal velocity is the temperature dependent velocity, and drift velocity is the external electric field dependent velocity. This is one line difference between, if I try to express the difference between these two velocities, then this one line is the ultimate difference, that thermal velocity is the temperature dependent velocity of charge carriers, and drift velocity is the velocity of charge carriers present in presence of an external electric field. So electric field based velocity. So this is everything. If you have any doubt regarding this, you can ask me in the comment section. I will definitely try to solve your question and solve your doubts. So thank you very much. Take care. Bye bye.